Hello, everyone. My name is Shanshan Zhao. I'm currently working as a postdoctoral researcher at SMU Power Electronics Center in Seoul National University. Today, the topic of my presentation is on the three-port bidirectional operation scheme of modular-multilevel DC-DC converters interconnecting MVDC and LVDC grids. My presentation includes 4 sections. The first one is the research background. The increasing penetration of renewable energies such as wind and solar, as well as massive demands for diverse DC loads such as electric vehicles, data centers, and energy storage devices, impose higher flexibility requirements on power systems. DC distribution technology can reduce the power conversion stages in the grid integration of the distributed renewable generations, energy storage systems, and DC loads. Besides, DC distribution presents remarkable advantages such as high efficiency, high power quality, and low cost of power cables, and thus has broad application prospects. The DC-DC solid-state transformer is a key component in DC distribution systems, which can realize the interconnection and support between DC grids. DC-DC SSTs can provide, firstly, voltage matching to adapt to different voltage levels in DC distribution system, and secondly, the galvanic isolation required for medium to high voltage applications. And lastly, it can realize multi-port operation, which adapts to the future trend of DC distribution system to multiple ports. Here is an example of DC-DC SSTs interconnecting multiple DC grids. Consider there is an urban MVDC distribution grid with 2 independent LVDC distribution grids with different nominal voltages. To interconnect such multiple DC grids, several DC-DC SSTs are required to access each LVDC grid individually in a galvanic isolated manner. Alternatively, a single DC-DC conversion stage capable of multi-port operation is preferable due to its compact configuration with higher power density and lower cost. To address this issue, the most widely accepted solution is the 3-port DC-DC SST based on a triple-winding transformer. It can realize the galvanic isolation between every 2 ports and at the same time realize the bidirectional power regulation of 3 ports. However, the transferred power of 3 ports in relation to phase shift angles are highly coupled. To realize the demanded power flow, multi-input, multi-output nonlinear equations should be solved, and that leads to significant computational efforts as well as stability challenges. Meanwhile, a circulating power among 3 ports dependent on the load profiles is inevitable, which increases the loss. Moreover, when a short circuit fault occurs at a port, the AC side of this port still has magnetic-motive force due to magnetic coupling, so that the fault current cannot be cleared by controlling the switching devices, and all ports need to be blocked. This results in low reliability. So next I'm going to introduce a 3-port bidirectional operation scheme. To address the aforementioned issues, the proposed operation scheme is based on 2 series connected double-winding transformers as shown in the right figure, instead of a triple-winding transformer. The primary side of the transformer windings are connected in series, while the secondary sides are connected independently to individual DC grids. Based on such structure, the transformer windings are not entirely coupled by the magnetic flux. And the DC-DC SST features the series current path. As compared with the figures, the triple winding transformer-based DC-DC SST has the parallel current path, which creates a circulating path for the current, denoted by the red line, while with the series current path, the circulating current is inherently prevented. In addition, the bridge circuits output positive and negative voltages on the AC side, which flexibly control bidirectional power of 3 ports. Another interesting characteristic is that ports with the same power polarity can be virtually combined due to the series current path, making the SST approximate a 2-port operation, and that makes everything familiar. Moreover, since the transformer windings are not entirely coupled by the magnetic flux, when a short circuit fault occurs, the bridge circuit of the fault port can clear the fault current simply by controlling the switching devices while maintaining the power transfer of healthy ports in a 2-port manner. With this concept, a 3-port bidirectional DC-DC SST is constructed for the applications of interconnecting an MVDC distribution network and 2 LVDC distribution networks. As shown in the figure, the multi-level converter is employed on the primary side to handle the medium voltage, which is denoted as port 3, and the full bridge is employed on the secondary side, which are denoted as port 1 and port 2 here, respectively. It is well known that the MMC has a variety of modulation methods due to its multi-level structure. This gives us the freedom to design the operation scheme which fully exploits the flexibility of MMC as well as the series current path. In simple terms, the goal is to mimic the classical phase shift modulation of 2-port DC-DC SST, which offers desirable power transfer capability while optimizing the transformer current. 2 operation modes are designed based on the power polarities of 2 LVDC ports, and the power characteristics are analyzed, which resembles that of a 2-port DC-DC SST, and thus can achieve simplified power control. Now let's take a closer look at how the operation modes are designed. When the transverse power of 2 LV ports at the same polarity, the SST operates in mode 1. The 4 bridges employ 3-level modulation, which output AC voltages with the same phase shift angle with respect to the AC side voltage of MMC, but with different duty cycles. The MMC employs 4-level modulation, which gives the same pattern with the sum of the secondary side AC voltages. In that way, the transformer current is in a flat-top waveform, and it can be proved by power calculation that the total power flow between the primary and the secondary side is determined by the phase shift angle. And the power distribution at the secondary side is determined by the duty cycles D1 and D2. Obviously, if one of the duty cycle is 0, then the port transfers 0 power, and the other ports can operate in a 2-port manner. However, that doesn't work when the two LV ports has different power polarities. Therefore, Mode 2 is designed. One way to change the power polarity of an LV port is to directly reverse the polarity of the AC side weightage. Moreover, the AC side weightage amplitude of MMC is reduced to match that of the secondary side, which effectively reduced the transformer current. Nevertheless, the transformer current will still be distorted. Considering the series current path, the ports with the same power polarity can be virtually moved to the same side, as shown in the equivalent circuit. Assuming LVDC port 2 and MVDC port 3 has the same power polarity, the equivalent AC voltage source of port 2 is virtually moved to the primary side. Then, the AC side voltages at the same side can add up to a square wave similar to a two-port DC-DC SST. To do that, the MMC and full bridge of port 2 are both modulated as three-level waveforms, and the full bridge of port 1 are modulated as two-level waveforms, as shown in the figure. The equivalent primary and secondary side voltages are both square wave, and the transformer current has a flat-top waveform. Based on the power analysis, similar results can be found, which is the total power flow between the primary and secondary side is determined by the phase shift angle, and the power distribution at the same side is determined by the duty cycles. In conclusion, in both modes, the total power flow between the primary and secondary sides is determined by the phase shift angle, and the power distribution at the same side is determined by duty cycles. In this way, the bidirectional power regulation of three ports is realized. The power regulation is greatly simplified and the transformer current is optimized. Since the proposed operation scheme strengthens the controllability of each port, the active control of the fault current can be further realized to enhance the stability of the system. The active control of the fault current can assist in the process of detecting and localizing short-circuit faults in the DC system, actuating the protection devices, and restoring normal operation. As shown in the figure, in stage 1, when a fault occurs, the DC link capacitor is quickly discharged, resulting in a high peak of the fault current. The SST should control the current injected to the DC grid to maintain the fault current at a preset level within the safe range until the fault is detected and localized. At stage 2, after the fault has been localized, the SST reduces the fault current to zero to de-energize the grid. At stage 3, the mechanical disconnectors are opened at zero current to isolate the faulty section. And finally, at stage 4, the SST re-energizes the grid after the fault is cleared. The system restores normal operation and the load can be reconnected. The control system is designed to realize the proposed operation scheme and fault write-through capability, which is mainly consists of a mode selection unit and a power control unit, including fault write-through control. When the power reference is delivered, the mode selection unit activates the corresponding operation scheme based on the power polarities and sends gating signals to the SST through PWM generation unit. Consider there is an MFC, so the PWM generation unit contains a modulation unit and a voltage balancing unit. If a short circuit fault occurs, the FRT unit detects the fault and activates the designed fault right-through strategy with active fault current control. Next chapter is to test the proposed operation scheme. First, the simulation result is presented. As shown in the figure, when the power command of port 1 remains 400 kilowatts and the power command of port 2 changes from 400 kilowatts to 0 kilowatts, the SST operates in mode 1, since the power polarities of port 1 and port 2 are the same. It can be seen in the figure that the transfer power of 3 ports are well regulated. And when the power command continues to decrease, of port 2 continue to decrease to minus 350 kilowatts, the SST operates in mode 2, since the power polarities become different. The transfer power of 3 ports is still well regulated, and the voltage and current fluctuations during mode transition when the power flow is reversed are quite smooth. This proves the effectiveness of the power control. And when the short circuit fault occurred at one LVDC bus, in this figure, port 2 is short-circuited. The SST switched to port operation. The original power transfer of non-faulty ports were maintained. In addition, the SST realized the active control of the fault current according to the design pattern. It can be seen that the fault current reached a high peak when the short circuit fault occurred at port 2, and the DC bus voltage of port 2 decreased to 0. With active current control, the fault current was maintained at the preset value to make time for the system to detect and localize the fault. After the fault was cleared, the DC grid of port 2 was re-energized by the SST, and its bus voltage returned to the nominal value. After that, the load was successfully reconnected and the system restored to normal operation. Next is the experimental verification. The experimental setup is shown in the left figure, and the steady-state waveforms are shown in the right side. The upper left figure presents the waveforms when the transfer power of port 1 is 150 volts and port 2 is 60 volts. The SST operates in mode 1. It can be seen that the phase shift angle of the AC side voltages of port 1 and port 2 are equal, while the duty cycle of the port with lower power is smaller. The upper right figure shows the result when the transfer power of port 2 is reduced to 0. It can be seen that its AC side voltage duty cycle is controlled to 0, and SST realizes a 2-port operation. The lower left figure presents the waveforms when the transfer power of port 1 remains 150 volts and port 2 is minus 30 watts. The SST operates in mode 2. The AC voltages of port 2 and port 3, which have the same power polarity, both employ 3-level modulation with different duty cycles. However, their AC voltage add up to a square waveform similar to port 1. Therefore, the transformer current has the flat waveform. Finally, the lower right figure shows the result when the transfer power of port 2 is further decreased to minus 60 volts. Obviously, the duty cycle of the AC voltage of port 2 increased and that of port 3 is decreased. However, the AC voltages still add up to a square waveform, and waveform of the transformer current is still a flat top. This result proves the availability of the designed operation modes. Next is the experimental result of the active power control. Similar to the simulation results, the experimental results also verify the effectiveness of the proposed three-port bidirectional operation scheme. Finally is the summary of today's presentation. A three-port bidirectional operation scheme of an MMC-based DC-DC SST for the interconnection of MVDC and LVDC grids is proposed. Firstly, the proposed scheme features simplified power regulation capability among three ports. The power flow of three ports follows a simple mathematical rule with significantly reduced computational burden, and the circulating current and the resulting losses are intrinsically prevented. Secondly, the proposed scheme realizes enhanced system stability with fault write-through capability. The fault current can be easily cleared while maintaining power transfer between healthy ports, and the active control of the fault current is realized to assist in the process of detecting and localizing the faults in the DC system, actuating the protection devices, and restoring normal operation. And that's all for today's presentation. Thank you, everyone, for listening.